Hello, everybody. I hope you are doing great. Today, we are going to continue to solve problems regarding electrochemistry. Here is the question. Two copper samples are immersed in a 1 molar copper sulfate solution. One is stressed to 200 megapascal in tension. We pulled the sample. Here, the other sample is unpulled. The other is unstressed. If the two samples are considered to be electrodes of an electrolytic cell, what potential is developed between the two? This is a beautiful question. This question belongs to MIT. It's very, very good question. I hope you will enjoy the answer. If I don't do any wrong. Elastic modulus of copper is 100,000 megapascal, density of copper 9.0714 gram per cubic centimeter. This is rounded value actually, and the mass of copper is 63.5 gram per mole. So we need to, what's going to happen is here, we need to sketch it first. Okay. Two compartments here. 1 molar copper sulfate, again 1 molar copper sulfate, identical. In terms of concentration, identical. And this one is also identical. This is copper plate. Also this one is copper plate, also identical. But there's a difference here. One is unstressed, and this one is stressed up to 200 megapascal. And what voltage are we gonna get here? Here's the question. It's a wonderful question actually. Here, let's remember mechanical behavior of materials. Sigma is equal to modulus of elasticity time strain. Let's remember here, the more stress we apply, the more strain we will get. Here there is a relationship between, according to Hooke's law, epsilon is equal to modulus of elasticity times strain, millimeter per millimeter, dimensionless, and this expressed in megapascal. You know, this tangent alpha gives us modulus of elasticity, okay? And the unit of modulus of elasticity is megapascal or gigapascal, okay? When we write down here, the stress is equal to E times the epsilon. The stress is equal to E times, this is the constant value, and this is dL over L0. And dL is the stress times L0. This is the initial length of the sample, and it's the modulus of elasticity. Okay, now let's look at the Gibbs free energy change, because something going on here. Same solution, same place, but the left compartment is unstressed, the right compartment is subject to stress up to 200 megapascals. So we are going to get Gibbs free energy change, and this Gibbs energy free change can be expressed as dt. S is the entropy times differential of the temperature plus volume plus differential pressure, and F, the force, because we apply force, and the L. And the temperature is constant. So dt is equal to 0. Pressure is constant. dP is 0. So d Gibbs free energy change is equal to force time dl. This is distance, difference in distance. Okay, instead of force, I can write down sigma times A0. Okay, so this free energy change is equal to sigma times N0 times, this is force, times dl d sigma times L0 divided by modulus of elasticity. So from this, L0 times A0 is volume. This is the volume of copper. Actually, molar volume of copper, and the molar of copper is about 7 cubic centimeter per one mole copper. Okay, let's continue. Delta G, difference in Gibbs free energy from 0 to 200 megapascal. E times sigma. This is stress. This is Gibbs free energy chain. This is stress and the stress. So stress, times 7 molar volume, 2 times 100,000 megapascal. From we solve the integral from 0 to 200 megapascal. And from this, delta G is equal to 1.4 joule. This is the difference between two samples. Difference in terms of Gibbs free energy between two samples. Now we continue. There is a relationship between delta G and E value of the system minus N F E. This is the number of electrons or valence value of copper, which is 2. This is Faraday constant, 96,500 coulomb. And this is the E value that we are after. Okay, we are after this value. Okay. And 1.4 is equal to minus 2 times 96,500 times E value. And from this E value is minus 7.25 times 10 to 3 millivolt.